In this video we're going to look at 5 rules for differentiation. 2 of them we've already seen. We haven't proven them. We've used them though already. They are the rules that say differentiation is a linear operator. And what a linear operator does is if you apply it to the sum, then that's the same as applying it to the pieces and then adding. Or if you apply it to a constant times a function, you can apply it to just the function and multiply by the constant. So we're going to, in this video, I'll prove the first one. It's very simple, but it gives you the idea behind the proof of all of them. You just restate what we mean by derivative. In other words, you use the definition of derivative, you do some rearrangement, and you get the right-hand side. We're going to separate out the proof of 3 into a separate video, and also we're going to separate out the proof of 4 and 5 into a separate video. So again, in this video, all I'm going to do is introduce them and prove the first 2. But before we even start the proof of the first 2, let's look at the others. This one is called the chain rule. The reason it's called a chain rule, and we'll see some more detail on that in a second, we think of this as being 2 functions chained together. First you apply g to x, and then you apply f to g of x. So it's a chaining of functions, and for that reason the derivative is, or this rule for the derivative is called the chain rule. Now the fourth one is called the product rule for obvious reasons. If you have the product of 2 functions and you want the derivative of that product, you can use this formula instead. And this formula says first take the derivative of f and multiply it times g without any derivative, just plain g, and then take plain f and multiply it times the derivative of g. So that's the product rule. We'll prove that in a minute or 2, or in the next video. Alright, now this one here is called the quotient rule because you have f divided by g. And it's sort of similar to the one above. You still have fg with a minus between them instead of a plus, and you still differentiate 1 on this side, the f prime. That's differentiated, and the g is just carried along. And then over here we have the g prime, and the f is just carried along. So it looks sort of like the top, except there's a minus instead of a plus. And on the bottom, there's actually a gx squared, where gx is the thing on the bottom over here. That's the denominator of the thing we started with. So that's the quotient rule, and we'll prove that in a second. But right now, let's just go back and prove this one here. This is one you could probably do yourself very easily, but it gives you the idea of how all the proofs work. So let's look at the details of that. Here is what we're starting with, the derivative of a sum. And we want to get from there down to here. And I've outlined the steps here, so you can stop the video and study them if you want to, but I'm going to go through them right now. And also, let me take note of this. I've actually defined some test functions so that we can do some numerical checking as we go along. And I've chosen functions whose derivatives we know. For instance, the sine of x, we know the derivative of that is the cosine of x. And this is a polynomial, and we know how to differentiate all of the terms of that, and that's this thing here. So, you know, in a way we're using the thing we want to prove to get this derivative. So it's a little bit of a circular reasoning, but not really, because this g could stand for anything. So we're proving this for an arbitrary g and just using the test functions as a numerical check. All right, so the first thing we do in all cases is apply the definition of this thing. And that definition is the following. The derivative is you evaluate the function at x plus h, subtract, well, I'm using f, in general, f here is f plus g. So you evaluate f plus g at x plus h, and then you evaluate it at just x. You take the difference and divide by h and let h go to 0. That's the definition. So if we apply that definition to this, we get this formula. So this is just f plus g evaluated at x plus h, and this is f plus g. Well, why is there a minus there? Because remember, we're subtracting f plus g. So that means each of the terms of f plus g get a minus in front of it. So this is just f plus g evaluated at x, these two terms there. Now what we're going to do is just rearrange. We're going to take this f of x here, and we're going to move it over. And then we're going to group these two things together. We want to think of them as a team. So let's just make that a group, and these two things as a group. Okay, so know what we've done, and this is what we do in general, is we apply the definition, we do some grouping, and then we just do some algebra. And the algebra is what we're going to do now. And notice this thing is a sum of two things divided by one thing. So I can distribute that h and divide both of the terms in the numerator by the same h. So I do that with my expand all terms, and we get this formula. But now look at this term here, this first grouping. As h goes to 0, that's f prime of x. And then the second grouping, as h goes to 0, that's g prime of x. So let's just make those substitutions. Let's pass to the limit. The first one is the definition of f prime as h goes to 0. So that becomes f prime, and the second one becomes g prime. And so we ended up where we wanted. So that's the nature of the proof of all of these. Apply the definitions, rearrange, do some algebra, and you end up where you want to be. All right, let's take the rest of this video just to do a little quiz, just to cement these things in your mind a little more before we get to the proofs. So I'm going to pop these up here. And stop the video and see if you can anticipate what the result is going to be. So what's this first one here? And I'm going to let the program do the job. Well, no, I'll do it myself. I'll do it by hand. So stop the video if you want to take a guess, and then I'm going to do it. So I'm going to do it right now. This is equal. Remember, the rule is this is a linear operator. So I can take that f, or that prime, and just apply it to each one separately. And I get the 1 down here, indicating I've got the right answer. All right, let's go to the next one. Again, stop the video if you want to quiz yourself. And notice this is the derivative of a product. The derivative is outside the brown parentheses. That means it's being applied to everything inside. And our rule says we can just carry the c along and apply the derivative to just the function. And in this case, we get it's approximately true. That's because the left-hand side is actually being numerically evaluated, and this program only assumes a certain h in evaluating this numerically. So sometimes you'll see, instead of a 1 here, you'll see something very close to a 1, but it's certainly okay. All right, now let's go to the next one. And again, stop the video if you want to test yourself. So I'm going to write it down. This is the way I remember it. I say, well, first of all, I'm just going to write down the two functions, f of x times g of x. Then plus, I'm going to repeat them, f of x times g of x. And of course that doesn't make any sense. Why would I write that? I'd just write 2 times f of x g of x if I wanted to. But you got to do one other thing. You got to prime that one and then go prime the other one. And there we see our 1. So that's a true statement. That's our product rule. Now let's look at this one here. This is our quotient rule. And the way I remember that is sort of, it's very similar to the product rule. So first of all, I just write down the 2 functions in the order that they're given there, times g of x, and do a plus f of x times g of x. And then I remember I have to make 2 changes to this thing. Well, before I even do that, let's do the same thing we did before. We prime the f, we prime the g, and notice down here, we're not there yet. We got to make 2 additional changes to our sort of product rule form. And the first change is to change that plus to a minus. And the second change is to divide everything by what? By f or by g? Well, by g, but not only by g, but by g squared. And there we have the 1. So that's the quotient rule. And now the chain rule. I don't think I even said anything about the chain rule, but let's look at the chain rule. Says if you're chaining 2 functions together and you want the derivative, you first take the derivative of the outer function. Let's call that f the outer function. That's the one you apply last. And g we'll call the inner function, or the first function. So you differentiate the outer function and evaluate that at g of x. But then you have to actually differentiate the inner function and evaluate that at x. So that's the chain rule. If you're chaining 2 functions together, the derivative is the product of the 2 functions, basically. But you got to remember to evaluate this first function at g of x. And we're going to see a picture for that when we actually prove this thing. It'll become a little, perhaps a little clearer why it needs to be in this form. Okay, so those are our 5 rules. The next video we're going to prove, well, maybe all of them. It depends on how long it takes. So we'll just have to see how many we can cover in the next video.